Welcome to Cosmology and Jesus. I'm Dr. Jeff Groh. I'd like to discuss today what people often ask me when I'm discussing topics like the Big Bang. What does space curve into? Einstein's general theory of relativity describes space as being bent. And the common question is, bent into what? The answer is nothing. Let me explain. Einstein's general theory of relativity describes gravity as the bending of space-time, the curvature of space-time. Curvature is a system of what are called metric relations. And those metric relations can be placed on any set, almost. You can even define a metric relation on a piece of the plane, something that is flat, and have it give curvature to that flat piece of space. The metric relations themselves give you this curvature. This is going to require a little bit of explanation. First, let's look at the Euclidean metric. The Euclidean metric is basically an extension of the Pythagorean theorem. A little change in x, a little change in y. You square those and add them up, you get the length of the hypotenuse of a right triangle. So ds is the length of the hypotenuse, dx is a little change in x, dy is a little change in y. So dx squared plus dy squared equals ds squared. That's the Pythagorean theorem. That's flat space. That's the sort of way you can measure things in flat space. However, flat space is not the only possibility. Before I move on, we have the Euclidean metric in polar coordinates. You can see here that we have ds squared is equal to dr squared plus r squared times d theta squared. Let's suppose that the little change in angle, d theta, is 0. If that's true, you can take the square root on both sides and get the little change in length is equal to the little change in radius. That kind of makes sense. The only way you're going is in the direction of the radius, making a little change in the direction of the radius, and so the change in length is exactly the change in radius. On the other hand, if you make dr 0, the little change in radius 0, you can take the square root of both sides and get ds is equal to r times d theta. S equals r theta, that's a formula that is commonly taught in high school trigonometry and geometry. The arc length along the arc of a circle is equal to the radius times the radian measure of the angle. If you put those two changes together, a little change in angle and a little change in radius, then the formula ds squared equals dr squared plus r squared d theta squared is the Euclidean way of measuring that total distance. However, there's a way of imposing metric relations on the upper half plane. X goes from negative infinity to infinity, but y goes from 0 to infinity, in such a way that we can impose a negative curvature on the upper half plane. The upper half plane is still just the upper half plane, but we're going to give it negative curvature by changing the way in which distances are measured. The common way to do that is to make ds squared equal to 1 divided by y squared times the usual Euclidean way of measuring distances, dx squared plus dy squared. It's not hard to show that the straightest possible paths under this new way of measuring distances are going to be arcs of circles that intersect the x-axis at a right angle, or vertical rays. To go from one point to another on one of these paths in the shortest distance possible, you either go straight up and down or along the arc of one of these circles. In this way, we can form what are called geodesic triangles. These geodesic triangles will have angles alpha, beta, and gamma, and because they're a little bit pinched, it turns out that the sum of these angles, alpha, beta, and gamma, will be less than 180 degrees. That's characteristic of objects that have negative curvature. A classical illustration of the Poincaré upper half plane is this representation by M.C. Escher. M.C. Escher is giving angels and demons. You can see the angels in white and the demons in the darker color. In the Poincaré upper half plane metric, all of these angels have exactly the same size. It's just that with this metric, but the distance from any point in the plane down to the x-axis is infinite. So there are an infinite number of angels and demons as you go down towards the x-axis. In another classic illustration, M.C. Escher had angels and demons on what are called the Poincaré disk. In the Poincaré disk, the shortest possible paths are again circular arcs intersecting the boundary circle at a right angle or rays going through the origin. The metric that gives you this geometry is this Poincaré metric. Here, I've illustrated a number of these geodesic paths. These are the shortest possible paths between points along those arcs. Here, the shortest possible paths between 2 points in the plane are along these circular arcs that intersect the boundary circle with a right angle or rays that go directly through the origin. Here, I have 3 of these geodesic paths that intersect, forming a geodesic triangle. Again, notice those angles, alpha, beta, and gamma, are pinched, giving a total angle sum less than 180 degrees. All of this results from something called the Gauss-Bonnet theorem, which says that the total angle sum is equal to pi, or 180 degrees, the total curvature. If the curvature is negative, then the angle sum will be less than pi, or 180 degrees. If the curvature is positive, that angle sum will be greater than 180 degrees. So you can see that the geometry of these triangles, the angle sum, will be dependent upon the curvature of the space in which they're embedded. Keep in mind, in both the Poincaré upper half plane and the Poincaré disk that we have seen, these are pieces of the plane. They're in the plane. We've just changed the way that distance is measured between points in this region of the plane. Another classic example of an object that has negative curvature is the pseudosphere. However, in this case, we're illustrating the pseudosphere as being embedded in 3-dimensional space, so it looks like it has curvature. When these 2-dimensional objects with curvature are embedded in 3-dimensional space, you can often tell if they have positive curvature or negative curvature by how they bend. You can see that if you have bending in one direction and the opposite bending in another direction, you get negative curvature. If you have the same kind of bending in all directions, the surface will have positive curvature. An illustration of that is the sphere. The sphere has positive curvature. Here I've drawn a geodesic triangle on the sphere. In this case, we have lines, geodesics, they're actually bent. But from the perspective of a person living on that surface, they wouldn't seem bent. You'd just go walking in a straight path from the North Pole, let's say, all the way down to the equator. You'd take a 90-degree turn at the equator and then march across to another point on the equator. Take another 90-degree turn and then march back to the North Pole. The 2 angles at the equator are both right angles. 90 degrees plus 90 degrees is 180 degrees. But wait, there's one more angle to add to that. So the total angle sum on this triangle will be greater than 180 degrees. So what does this have to do with cosmology, or Jesus for that matter? Well, today we're focusing on geometry, and geometry has a lot to do with cosmology. That's because Einstein's general theory of relativity says that the curvature of our space-time is directly proportional to the mass, energy, and momentum of the space-time. His theory turned geometry from a deductive science into an empirical science. We can now determine physically what the geometry of our space-time is. by measuring it. And it turns out that these geodesic triangles around massive objects in our own universe will have angle sums that are strictly greater than 180 degrees. This is an empirical fact. And so that begs the question, what is space curving into? And the answer is nothing. Gravitation affects the metric relations between points in space. As we've seen, regions in the plane can be assigned metric relations that give it a negative curvature. So what's going on with gravity? The mass, energy, and momentum in our space-time affects the metric relations between points in our space-time. Space doesn't have to be curving into anything. And so that's it for our short discussion today. If you like this, please like, subscribe if you so choose, and if you'd like, give a small donation